We're now going to move to our second synchronization issue, which is ensuring that we have memory consistency. And if you remember, that's a happens before relationship. We want to ensure that one thread executes before another thread. And coordination, there's three times or three things that can lead to coordination breaking down. One is deadlock, where two different threads have two different locks, and each is demanding the other's lock. So in essence, what we have is that perhaps thread A has a lock on object 1, B has a lock on object 2. Now B needs access to object 1, so it needs to obtain object 1's lock, so it blocks waiting for A to release its lock on object 1. However, A, in order to complete, needs object 2. It needs that lock, so it also blocks, waiting for B to release its lock. They both end up blocked, waiting for the other process to finish, and we end up with deadlock. I'll give you another example of that in a moment. We have also starvation, where one process may be hogging the synchronized method, especially if a synchronized method takes a long time. And if that method is utilizing, or if that thread is utilizing that method a great deal, it cause other methods to starve, especially if they're looking to use other synchronized methods in that object that aren't as time consuming. And finally, live lock doesn't occur as frequently, but it happens when you have two threads, A and B B takes some action that A has to respond to. So A starts to respond, but as it responds, that causes B to start to respond to the action from A. It's like if you and I are approaching each other in the hall and we're on a collision course, I might move to the left to avoid you while you simultaneously move to the right to avoid me. Well, we're now still on a collision course, so perhaps I now move right, but you simultaneously seeing the problem also move left, and we're still on a collision path. So this is live lock, where we spend all of our time trying to respond to each other and we're not getting any useful action done in between. The most common problem is deadlock and trying to avoid deadlock. So let's just take a look at a sample of how deadlock can arise. And we're going to take the example used in the Java concurrency lecture, where we have Alphonse and Gaston, who are friends and believers in courtesy. So they believe that if you bow to a friend, you must remain bowed until your friend has a chance to return the bow. So we're going to assume here's Alphonse, here's Gaston. So Alphonse bows to Gaston, which means Alphonse has to stay bowed until Gaston bows and then comes back up. Well, what happens if both Alphonse and Gaston bow at the same time? There's kind of deadlock there because neither can rise until the other finishes bowing. And so to simulate that, we have a class called friend, and we have two synchronized methods, bow, where we're going to bow to our friend, and bow back, where our friend bows back to us. So in bow, we simply print out a statement saying that so-and-so has bowed to me, and now I am going to bow back to that bower. And in bow back, I'm simply indicating that such and such has bowed back to me. So now I create two objects, Alphonse and Gaston, and I start running them. Each of them is going to start by bowing. So let's trace what happens. We're going to create two objects, one for Alphonse and one for Gaston. So we're calling Alphonse.bow right here, and in Alphonse's thread. So he calls bow, and he's got Gaston's object. So we're just going to call that G for Gaston's object. And he starts executing bow, and he calls this format statement that's going to print out the statement that Gaston has bowed to me. And notice that he has a lock on himself because bow is a synchronized method. So now Alphonse blocks on the format statement, gives up the CPU, and Gaston gets the CPU. His thread gets the CPU. He calls bow with Alphonse as an object, so he gets the lock for Gaston. And now he also calls this format statement to indicate that Alphonse has bowed to me. And so he blocks, and Alphonse, having completed the format statement, comes back, and Alphonse tries to call bower, which is G.bowback. Now the problem is Gaston already has the lock for G, so Alphonse blocks, waiting for Gaston's lock. And now Gaston comes back from his format statement. He tries to call back on Alphonse, but Alphonse has the lock, so Gaston blocks, waiting for Alphonse. Now they're both blocked. Neither of them is going to be able to finish and release the lock, and hence they're in deadlock. How can we coordinate our actions and avoid these deadlock conditions? And also, how can we ensure that we force, say, thread A to execute before thread B? The way we can do that is by giving up our locks sometimes. And the way we can do that is using the wait method. The wait method will suspend execution until another thread calls either notify all or notify. And in calling wait, we give up our lock and allow some other method to acquire the lock and to start executing. Now, this actually will allow some other synchronized method to get called while we are waiting. Now, when we suspend execution, we're going to be writing out our register variables so that they will be visible to someone else who comes in at this point and calls the synchronized method. Also, we should only call wait when we're at a point where we're not in an inconsistent state. We're okay with some variable being changed. Secondly, when we are awakened by a notify or notify all command, we have to check to make sure that the condition has actually changed. The reason is that, first of all, we might have had multiple threads block on for some reason. And when the notify method comes, all the methods may be awakened with notify all, yet only one of the conditions may have become true. So for example, let's say that we have maybe threads A, B, and C all waiting on different conditions, and D perhaps changes the condition that allows B to proceed and then calls, let's say, notify all. Well, A and C should not proceed, only B should proceed at this point, so they all need to recheck their conditions. Also, notify arbitrarily selects one thread to wake up. There's no way to specify the thread you want awakened. So when D calls notify, perhaps A gets awakened. A checks the condition, sees that it's still not satisfied, and recalls wait. Then maybe C might get awakened. It checks its condition, finds out the condition's not satisfied, and waits. And finally, B is awakened, finds the condition is satisfied, and continues. So it's always important when you wake up from a wait to check and make sure that you've actually, your condition is the one that's been changed. Here's an example of how you should be writing your wait statement. So we are assuming there's a variable joy that needs to be set to true before we can continue. So we have a happens before relationship where thread 1 is going to wait until thread 2 has set joy to true. So we write a while loop. It's not a busy wait loop, but it is doing a retest. So it's first optimistically checks joy, and if joy is true, we would never execute this while, and we would print the statement joy and efficiency have been achieved. However, if joy is false, we'll now go into this loop where we will wait, and wait throws a interrupted exception because we could be interrupted during this time. Someone may get impatient with us, so we need to catch that. In this case, we're doing nothing, but we might also decide to do something else like return. So we wait, and when the notify comes, we come back and we test joy because that's the condition we're interested in. And if it's now true, we will again print out joy and efficiency have been achieved. And over here, we see that thread 2 is calling notify joy, which is another synchronized method in our class. It sets joy to true and then notifies all to wake up any methods that were waiting to get back started again. Now notice that we were in the middle of a synchronized method in thread 1, but by calling wait, we released the lock, thus allowing notify joy to be called by thread 2. Also, nothing had happened in thread 1 that was going to conflict with what thread 2 was doing. Thread 1 was going to wait explicitly until thread 2 had set joy. It turns out that the wait method is not a particularly good way to resolve the deadlock between Gaston and Alphonse. So we will put that off until another lecture when we talk about Java's locking mechanisms. So to give you an example of how wait can operate, let's take a look at the producer-consumer example where we have two cooperating processes. We have a single item. So we're going to have what we're going to do is we're going to have a so-called drop box, and it contains a single item. So the producer is producing items randomly for this drop box, and it's putting items in there, say a message. And then the consumer is supposed to be withdrawing these messages and printing them or doing some processing with them. Well, because there can be only one message in there at a time, if the producer sees that this drop box is already full, the producer should not produce another message, but should instead block until this box has been emptied by the consumer. So this is perfect for wait on both sides. The producer will wait if the drop box is full, and the consumer will wait if the drop box is empty. And in each case, the consumer will issue a notify command or a signal when the consumer consumes the object in the drop box, and the producer will generate a signal when the producer places something in the drop box. That's the general idea for our producer-consumer example. Now let's take a look at the actual code. So we're going to define this class drop, and it's going to have our message. That's the thing that's being filled by the producer and consumed by the consumer. And now we're also going to have a variable that indicates whether the box is currently empty or not. And this is going to be toggled by the producer and the consumer. The take method gets executed by the consumer. It returns the string, and it's synchronized. So we are going to wait until the box is full. And while it's empty, we're going to wait. And when we catch a signal, we need to check and make sure that that it's actually not been emptied by some other consumer. So if there are multiple consumers that could call take, it would be dangerous to just assume when we're awakened that we can read the message because some other consumer may have already taken it. If we do wake up and it's empty is false, we now set empty to true because we're taking the message. We notify the producer or any producer that it's empty and it should be refilled, and then we return the message. The put method is called by the producer and it will fill up the box, and again it's synchronized. The producer has to wait until the box is empty, and if it's not empty, it will wait. Again, when it's awakened, it can't just assume that the box is empty because perhaps the drop box was filled by another producer. But if it is empty, it comes out and it now sets empty to false and stores the message it was given into the drop box, and then it notifies everyone that the status has changed. Notice if there was other producers waiting on this, if there were other producers waiting on this object, they would also be awakened at this point, and it would be important that they not execute. Hence the importance of having this while statement here. Then the producer thread is implementing a runnable, and it's going to be given the drop box, which it's going to share with the consumer thread, and it's got a set of messages that it's going to store into the box, and it's going to generate them at random intervals. So it's going to use a random number generator that's going to generate a random number. We iterate through the array of messages, and we put each message in, and notice we will block because the put method will block if necessary. And then when it's done, we will sleep for some time between 0 and 5 seconds, and when we wake up, we will increment I and print the next message until we've iterated through all the messages. And when we're done, we are going to do one more thing where we put done into the drop box. The consumer is going to keep reading messages. So here's the consumer. They also have the drop box, the same drop box right there. They also are going to have a random number generator for randomly picking up the messages. They are going to have a slightly different for loop. They don't know in advance how many messages will be generated. That's why the producer generated a done message when the producer was done. And we start by initializing our message to the first message we receive. And after each message has been processed, we ask for the next one. And what we do is we format or we print the message, and we then sleep for some random amount of time between 0 and 5 seconds before waking up and trying to process another message. And finally, the main method simply creates a drop box and then passes that drop box to each of the producer and consumer threads and starts them up. There is a second lighter weight way that we can try to enforce a happens before relationship, and that is using volatile variables. Now, they have primarily been superseded by atomic variables because atomic variables can do more in terms of incrementing values. They can also, as we saw earlier, they're able to compare a value with a previous value and only update if the two values are equal. However, volatile variables are very lightweight. They don't have the overhead of classes, which atomic variables do, and they operate just on reads and writes, and they force any change made by a thread to be forced out to main memory. So it can't be held in a register, it's forced out, and it eliminates the need for synchronizations and happens before situations. So here's our previous example, but we've moved synchronized from our two methods. They're no longer synchronized because instead we're simply using a volatile variable joy. And now when notify joy sets joy to true, that is a atomic operation that's going to force the value true to be written out to joy, and now it notifies all. And over here in guarded joy, we were happy to wait until joy is set to true. And so the fact that it's finally forced out is going to allow us to now continue and print out joy and efficiency have been achieved. Now, if this volatile were not here, then thread 1 would get a value of joy that it would keep in a register, as would the notify joy over here. And now we have an issue because when thread 2 modifies joy, it gets written to this register. Now notify joy would exit, but the problem is that the value would not be flushed, and we would end up over here with just a local value, the register value for joy, and joy, when we wake up, would still see the value false because it's in our register, so we would immediately go back into wait, and we would never wake up again because over here thread 2's done its job, it's exited, it's never going to call notify all again, and so guarded joy is eventually going to starve. There's no deadlock here, but it's going to starve. Synchronized, when we put synchronized here, that took care of the issue because remember, synchronized forces the values to be read from memory after we reacquire the lock. So synchronized would allow us to succeed in this situation. However, by putting a volatile right here, we can also succeed without using the heavyweight machinery for the synchronized command. Again, volatile is not used very frequently anymore. It would be more likely for us to use the atomic variables if we wanted to do some kind of implicit synchronization. Remember, this is an example of implicit synchronization because we don't have the explicit synchronization blocks here. This concludes our discussion of synchronization mechanisms. We've discussed 3 mechanisms: synchronized methods, atomic variables, and synchronized statements for preventing race conditions. And we've discussed 2 techniques: wait and volatile variables, for ensuring happens before relationships, which ensures that we have memory consistency.